Welcome, ladies and gentlemen, welcome back. Now we're looking at a different portion of continuity. We're looking at the theorem, and we're going to look at this step by step. We're going to pull in the definitions of continuity in the theorem that we just finished looking at, and showing all these statements were equivalent, and they were the same thing as saying that a function is continuous at a point A if the limit of f of x as x approaches A is equal to f of a if the limiting value is the same thing as the function being defined at that value. So here goes the theorem. If f of x, I need my professor's stick. I knew something was missing. You ever had that happen? You leave home, get your cell phone, and you go like, oh my God! I need my professor's stick. I gotta have this. Power. Oh, okay. So here we go. Theorem. If f of x is differentiable at A, if we can differentiate the function at A, then f of x is continuous at A. So what am I going to do now? Based on previous behavior, what am I going to ask you now? 1? Very good. Excellent. Oh, you guys figured me out. Yes. Now I'm going to ask you to pause the video, copy the theorem, then we're going to move on. Class, please copy the theorem. Thank you, Juan. Bernardo, Maria, Luis, thank you. Go ahead. Please copy the theorem. Okay? Thank you. Alright, at this point, if you have not copied the theorem, please pause the video and do so. I will pause the video now. Okay, ladies and gentlemen. So now we want to show that if this function is indeed differentiable at A, it's continuous at A. Question. What's the algebraic representation of showing that a function is differentiable at a point? Go back and look at your book for a minute. Let me let you think about that. What is the algebraic expression for showing that a function is differentiable at a point? Let's see. Peter? Okay, very good. What about you? What expression do we use? What is it called? And you saw this in your pre-calculus class. It had a specific name to it. What is it called? Let's see. Luis. Very good, yes. It's called the difference quotient. For those of you who took pre-calculus, it's called the difference quotient. So let's see what it looks like. So, if, starting out proof, if f of x is differentiable, if it is indeed differentiable at A, then we had the following. The limit of f of x of f of A plus delta x minus f of A divided by delta x as delta x approaches 0. And here's the key word, ladies and gentlemen. If this function is indeed differentiable at A using this expression, here's the key word, then this limit exists. And I personally would put in here to really stress that must exist. It must, and let me put this in capital letters because paying close attention to our wording is extremely important. So, and let me put this in red. So, if this is indeed differentiable at A, then this limit must exist. So it must exist. It has to exist. So I told you I want to examine this piece by piece by piece. Okay, class, are there any questions? Because if it's differentiable at A, then this limit has to exist, because if it does not exist at that point, then you can't differentiate it. It means it's undefined. It's either, the denominator is either 0 or it's a vertical line. You can't take the derivative of a vertical line because slopes of vertical lines are undefined, because the derivative is just another way of looking at slopes of tangent lines along curves. So this is another way of showing a slope. Any questions? Do you have any questions? So this is the first part of our theorem. That if f is indeed differentiable at A, then this limit, it must exist. It has to. And key word, let me underline that. You must pay close attention to words. Exists. These are some of the things that I missed when I was in high school and studying this and went on. That's what I'm saying. You need to go back after we finish, review this, get a cup of cocoa, sit back, close your door, and get everything else out of your way. And just focus on this. Think it over. Think over what I'm saying to you and highlighting. That is extremely important. Okay. Well, my next question to you is, all right, so what? Okay, f is differentiable at this. It's differentiable at A. We now know that this limit exists, but how do we show that this proves this function is continuous at A? So right now we said that in order for this to be true, we're going to assume that this hypothesis is true. We're going to accept it as truth. So we're going to assume that it is differentiable at A and that this limit of differentiation does exist. So what? This still doesn't prove to us that it's continuous at A. So how am I going to go from here that it's differentiable to showing, because it's differentiable, that it is continuous at A? Class, I want you to think it over. I want you to think it over. And let's see, who am I going to call on next? Patricia, I want you to think it over. You're going to be point person on this. Collaborate with your other classmates. And then I'll get back to you about 1 or 2 minutes. I want you to think it over. How we're going to show that this differentiable expression also means that it's continuous there. Let me give you a minute or so. So you guys go collaborate, and I'll get right back to you. I'm going to pause the video. I want you to really think it over first before you continue on with the rest of the class. Is that good? Okay, think about what I said. Okay, ladies and gentlemen, here goes the critical part. In order to prove that this differentiation expression also shows that it's continuous at that, we're going to have to call on the definition of continuity. And what I'm going to use the fourth statement that we covered previously when we showed 4 different ways of writing the definition of continuity. So we need to pull from the definition of continuity and then do some algebra to arrive at the differentiated function to show that because it's differentiable, that it is continuous. So here goes the fourth statement. Let's call on the fourth statement. Here was statement number 4 that you were given previously. The limit of delta f as delta x approaches 0 is equal to 0. Now we just saw that we know what delta f is equal to. Well, delta f can also be written as the limit of f of a plus delta x, okay, minus f of a as delta x approaches 0 is equal to 0. So now revisiting our line segment, here's A. I'll make this a little smaller. Here's x. And here's delta x, our increment. So what this is saying is that as delta x is getting smaller and smaller and smaller, infinitely small, the distance between x and a is getting so small that you definitely need to have an electron microscope to see what distances remain between them. This is critical to getting into understanding the foundation of metric spaces. When you get into the higher level, we start calling it a deleted neighborhood. So as this space gets smaller and smaller and smaller, what this says that it eventually, that if it is continuous at A, that X is going to overlap A. There is no distance between them because now they are one and the same. So therefore, the difference between these is 0. Therefore, that function is continuous at A. So we're going to use the definition of continuity to prove that when a function is differentiable by this expression, that it is continuous. And remember, by the definition, this says that the limit of delta f as delta x approaches 0 is equal to 0. This is the critical part that I even missed through some of my years of studying calculus. That is the critical part. That is what the definition of continuity tells us. That the limit of delta f as delta x approaches 0 must be, has to be, 0 in order for a function to be continuous at a given point. Or the limit of f of a plus delta x minus f of a as delta x approaches 0. As this distance shrinks and gets smaller and smaller and smaller and smaller and smaller and smaller, it gets so small, you need the most powerful electron microscope to see if there's any distance between those two. That it gets that small, you can say that the distance between these is 0. Therefore, if it is 0, then you can definitely say that it is continuous at that point. Please, this is the critical part in the proving that if a function is differentiable at A, then this shows that it is continuous at A. This part of the definition, I don't want you to miss it. It is critical to your understanding to see how this piece fits into that. How we're going to use that. Critical. So now, let's take the definition of continuity and let's show that. So I'm going to start with this. Is that all right? Okay, here's how we're going to do this. So now, here's what we have. I have the limit. Oh, wrong color. Wrong color. So I'm going to rewrite this. So now I have, using delta f, using this expression that represents delta f. Here's what we're going to have. We have the limit of f of a plus delta x minus f of a as delta x approaches 0. Okay, copy that please. And remember, we're going to use this definition of continuity in order to prove that this does show that it is continuous. Copy that please. Juan, Maria, Peter? Any questions so far? Am I going too fast? Is it a good pace? Very good. Please. Okay, now here's what we're going to do now. Now we're going to apply a little algebra.